Thank you. This is joint work with Rakicon done while he was visiting UIUC. And it involves presenting what is designed as a simpler approach to indentation sensitivity than what we're doing right now. Hopefully something that will be simple enough that you could use it in the smallest domain-specific language, while still also being expressive enough to handle these sorts of indentation we see in Haskell. So, my clicker is not working. My clicker is not working. Thank you. There we go. Okay. As we all know, Haskell, great indentation-sensitive language, but it's not the only one. There's lots of others. For example, Landon introduced the concept 50 years ago with IceWin. Python's very well known for this. F#, the YAML data markup language. There's many other languages that include this concept. But there's a little bit of a... What? One more?
COBOL.
COBOL. Oh, okay. I'm going to have to add that to the list. I'm not sure about the company I want to keep there, though. So, one problem with all these languages, though, is they all use differing approaches, differing ad hoc approaches to solving indentation sensitivity, both in their implementations and even in their specifications. And to just give you an idea of what we're talking about here, I'm going to show you a little bit of an overview of how Haskell handles its indentation sensitivity. The language report specifies indentation sensitivity in terms of this L function that has to get inserted between the lexer and the parser. And the understanding is that the lexer is going to omit these magic in curly brace and in angle brace tokens that this L function is then going to resolve into explicit semicolons and curly braces so that the parser doesn't have to think about layout. It's just going to parse as if the user had written explicit delimiters all along. To go into a little more detail, the lexer is expected to emit an in curly brace token after any of the occurrences of a let, do, where, or of keyword, where in is the column at which the next token occurs. And this represents, sort of philosophically, a place where a new indentation block might need to start, so the L function might need to insert an open curly brace. Correspondingly, an in angle brace token will be inserted at the start of any new line, and this sort of represents where the L function might need to insert a semicolon or a closed curly brace. Already we can see a few problems here, though, in that both of these rules are entirely lexical. They don't take into account any of the syntactic context in which we are. So if you're embedding one language inside of another that may have different rules about how indentation sensitivity works, you're going to have a bit of a problem here. Even more so, there are certain syntactic constructs that can't even be expressed in this model. For example, if I have a construct where I want to say, if I've got an if followed by an open parentheses expression close parentheses, then after that close parentheses, I want to start a new block. I can't do this because the first rule means that I have to have a keyword that's just before the start of that indentation sensitive block to flag the fact that I'm starting a new layout block. But ignoring those problems and moving on, let's see how this works in practice. On this bit of code, what the lexer is going to do is it's going to emit five curly brace after that occurrence of where, because the next token is loop, and that's a column 5. Same for the second where, that's going to go to 9, and 9 angle brace and 5 angle brace. Then what's going to happen is that the L function is going to run. I'm going to come back to how this is implemented. But on this piece of code, what the L function is going to do is it's going to convert that 5 into an open curly brace. Same for the 9. For the 9 angle brace, it's going to convert that into a semicolon. And for the 5 angle brace, it's going to convert that into a closed curly brace followed by a semicolon. Finally, we're going to end up with one last closed curly brace to close the whole thing out. At this point, we fully resolved the indentation of our syntax we fully resolved the indentation of our syntax into explicit delimiters. We're just using semicolons and curly braces. And so in the grammar, we don't have to think about layout. The grammar just uses these explicit delimiters as if those were what the user had written all along. And as a result, this code gets parsed according to the block structure that we expect to have. Now, let's look at this L function again, because that seems to be where all the magic is happening. The L function takes in the stream of tokens, TS, from the lexer and emits a stream of tokens that are going to go to the parser. Along the way, it's passing along this MS, which is a stack of indentations that it uses for bookkeeping. The first case is when it sees an n angle brace token. So we started a new line. Well, if that n is equal to m, the current indentation context, then we're lined up with the current indentation context, so we're starting a new statement. So we're going to insert a semicolon. Correspondingly, if we're at a smaller indentation, then we moved out of an indentation block and we need to close the current block. So it's going to insert a closed curly brace. It's also, however, going to pop an element from that indentation stack. So you see, instead of passing m:/ms, we're just passing ms. If neither of those is the case, then we're further indented than the current indentation block. And so we're really continuing the same statement, and we don't need to do a whole lot. For in curly brace, what we're going to do is, well, we're starting a new indentation block, so we're going to insert an open curly brace. But because we started that new block, we're also going to have to push that context onto the stack, so in gets pushed onto the ms stack. Okay, so far so good. Then it gets messy. I'm not going to go through, I don't have enough time in a 20-minute talk to explain this, but I do want to point out this m-parse error t. Now the language spec says that what m-parse error t does is that if the current set of tokens emitted by the L function plus the next token, in this case t, is an invalid prefix of the Haskell grammar, but if I were to emit a curly brace instead, that would be a valid prefix of the grammar, then parse error t needs to return true. Well, what that means is this nice pretty diagram we had before with the lexer, the L function, the parser, that's not the whole story. There's a back edge, a reverse dependency. The L function needs to know what the parser is going to output so the L function can know what it should hand to the parser. And for this reason, most Haskell implementations don't use this structure at all. GHC, for example, it doesn't have an L function. Instead, it interleaves the execution of the lexer and the parser, and there's some shared state, and there's this protocol involved, and it gets messy. So in this paper, we propose a more principled approach to indentation sensitivity that we claim scales down and is simple enough and easy enough to use in even the smallest domain-specific language, while still being expressive enough to handle the indentation rules of Haskell. We implement this in terms of Parsec by observing that Parsec is actually a variation of PEG, and you can download that code. We validate its effectiveness both in terms of performance and correctness on a real-world language. So our basic idea is as follows. Well, first what we're going to do is we're going to have the lexer. It's going to annotate every single token it emits with the column at which that token occurs. Now hopefully that's not too onerous, because you're probably already doing that for error reporting purposes. Then in the parse tree, we're going to annotate every non-terminal and terminal with the indentation at which that occurs. So for example, in this code we had before, we sort of have these three regions of indentation at which are occurring: the blue, the green, and the red. And the blue is aligned to column 1, the green is aligned to column 5, the red is aligned to column 11. And what we're going to do is we're going to take all the expressions in the blue region and say they have indentation 1. All the ones in the green region are going to get indentation 5. The red region, they're all going to get indentation 11. Note very importantly here that when I talk about the indentation of the expression, I do not mean the column at which the first token in that expression occurs. For example, the recursive call to loop, the first token in that is the loop token, and that occurs like column 20 or something. But it's within the red region, so the indentation of that expression, I give the indentation of that region, which is 11. Then what we're going to do is we're going to annotate our grammar and say what are the valid ways that we could annotate indentations to our parse tree. So to see this in action, I'm going to use this small little domain-specific language. Well, if you recognize what it is, it's not quite so domain-specific. The rules for this language are going to be that the right-hand side of equality starts a new indentation block that is aligned to the column of its first token. And inside of a parentheses, we're going to allow ourselves to reset the indentation. So this is similar to how in Haskell, if you have curly braces, you can reset the indentation back to the first column. And we've got a little bit of code down here that demonstrates this, and here's the corresponding parse tree. So what we're going to do, first we're going to annotate all the terminals with the column at which they occur. Then we're going to take all the expressions in the blue region, annotate them with the indentation of the blue region. Same for the red region, are all going to get annotated with the indentation of the red region, and the stuff in the green region for the same. Okay. Now we need to specify the rules for how indentation is going to operate. And we're going to specify the rules that tell us whether those annotations we put on the non-terminals are actually a valid way to annotate this. So for all the terminals are allowed to occur at any column greater than or equal to the current indentation. So for example, the identifier V, that occurs actually at column 5, but it's part of the blue region. But that's okay because a terminal is annotated with a greater than or equal to. And you can see here in the parse tree how it's a descendant of an expr at 1, but this is allowed due to the parse because we use a greater than or equal to. Similarly, most expressions don't actually involve indentation. So for those, we want to keep it the same because we don't want to start a new region. So we're going to annotate those with an indentation relation of equality. For the cases where we do want to adjust our indentation, for example, the right-hand side of equality, we're going to annotate it with a greater than or equal to indentation. So for example, the right-hand side of that equality, that occurs at indentation 6, which is allowed because it's greater than or equal to the indentation of its parent, which is at 1. Similar thing happens for the inside of parentheses. Here I need a new relation called splat that just relates all integers to all integers. And this allows me to put expr at 0 when its parent is at 6. Now, we're almost done. There's one last thing. Remember I said at the beginning, while it's not always true that you want a non-terminal to align to the column of its first token, in many languages there are certain constructs in which you do want this. And remember I said at the beginning, for the right-hand side of expr, we do want it to align to the first column. In this case, the minus sign. So what we're going to do is we're going to introduce one more operator, which is this absolute alignment operator. And what that means is that down the path, leftmost path to the first token, all of those terminals and non-terminals must have the same indentation as each other. So in this case, this forces that right-hand side of the equality to actually be at indentation 6, so that it matches the indentation of the minus token, instead of being at something like 3 or 2 or whatever. Okay, now at this point, we've actually fully specified the indentation rules for our language. But we've kind of cluttered up the grammar with all these annotations and whatever. But we can fix that with a little bit of syntactic sugar by first observing that all of the terminals, they all have the indentation relation of greater than or equal to. So what we're going to do is we're going to allow a default. So if I don't annotate it implicitly, I mean greater than or equal to. So those go away. Similar things happen with most expressions. Those are almost all equal. So if I allow that as a default, those go away. And now at this point, we actually have a very compact and simple notation for specifying the indentation rules of this language, in which you only have to mention the indentation operators at those points in the language where something interesting happens with regard to indentation. Okay, so we wanted to implement this idea in Parsec. Well, as we observed in the paper, Parsec actually turns out to just be a variation on PEG. So the question is, how would you implement this in a PEG parser? Well, the way PEG works is that it's a rewrite relation from a parsing expression P and an input word W to a step counter N, which is just used as a metric for proofs, and a result O. Now that result could either be bottom for a failed parse, or it could be top for a successful parse. If we are successful, the result also includes the prefix of the input string that we consumed. Now if you do this, the PEG parser ends up being fairly straightforward and what you would expect with the typical combinator-based parser. So if you're consuming a token, you check if the first token is the token you want, and you consume that and you move on. If you're doing sequencing, you just thread the string through. If you're doing choice, you attempt the left-hand side, and if that fails, you try the right-hand side. In order to generalize this to indentation-sensitive parsing, what we're going to do is first we're going to annotate all tokens with the column at which they occur. Then we're going to pass along this indentation set. And when we pass the indentation set in, what this represents is at what indentations we want to attempt to do a particular parse. Then that indentation set will actually come out in the output, and that will represent at what indentations the parse did succeed at parsing. Finally, in order to handle the absolute alignment operator, we're going to introduce one more flag which tells us whether we need to be enforcing the absolute alignment rules. If we do this, almost all of the PEG rules basically stay the same. Okay, there's this little bit of extra state you have to thread through, but nothing particularly surprising happens. The only interesting cases are these here on this slide. First of all, when we've got a terminal, what we have to do is not only check whether the terminal we're parsing is the one that's next in the string, but we also have to check to see whether that next token in the string is at one of the indentations that we're attempting to parse. If it is, then we return that indentation as a singleton set, and we also clear the absolute alignment flag, because once we consume one token, we don't have to continue to enforce absolute alignment. Now, in order to handle the greater than and the greater than or equal to operators, we generalize to a local indentation operator for an arbitrary relation triangle. And what we're going to do is we're going to take the indentation set n and say, hey, we're moving to a place where we could go to a greater than or equal to set of indentations. So we're going to find the set of indentations that match some element of the original indentation set I according to the relation triangle. That gives us this new indentation set j that we're then going to pass into the parse. When that parse eventually succeeds, it will hand back this j prime, and then we're going to go back and say, okay, which of the i's could we have used that results in this j prime that's still related by the triangle? And then we're going to get back this I prime that we're going to then thread back out. At this point, handling absolute alignment is actually almost trivial. All we have to do is when we see the absolute alignment operator, we first set the absolute alignment flag. Then when we have one of these local indentation operators, what we're going to do is, if the absolute alignment flag is set, we don't want to change the indentation set. So we actually just ignore the local indentation operator. And it's only in those cases where the absolute alignment flag is not set that we do this ij calculation. So we implemented this in Parsec, but we wanted to test to see how effective it was. So we modified the Idris language to use our technique. And the nice thing about Idris is it already had an ad hoc implementation of indentation sensitivity. So we could compare our implementation against theirs. And if you look at the grammar, we actually end up with something much simpler. The number of lines of code in the grammar related to indentation sensitivity were about half as much in our grammar compared to the original one. We also wanted to verify we were still being correct, so we ran this new parser, this new implementation, against a large collection of Idris code. And, well, to our surprise, we got some differences, which concerned us for a little bit. There weren't many, but there were a few. So we looked into those, and it turned out they were all due to fairly obvious bugs in the, not that they were obvious to find, but they were obviously bugs in the original Idris implementation. So for example, we found this bit of code. The Idris parser original Idris parser will fail to check the indentation of that m plus token. And as a result, it'll parse those last two lines as being part of the same statement, even though the indentation of that last line means it can't even be inside the innermost do. We also ran performance benchmarks. Now, originally, we were about 2 times slower than the original Idris parser. We investigated that and found a few tweaks that allowed us to bring down to these results, which allow us to match the original Idris parser. Details on that are in the paper. So, in summary, we present a principled approach to indentation sensitivity that is simple and easy to use. It scales down to the simplest domain-specific language while still being expressible enough to handle large-scale languages like Haskell or F# or Python or Agda or Idris, etc., etc. We've implemented this in Parsec by observing that Parsec is a variation of PEG, and you can download the implementation on Hackage. We benchmarked and validated both its performance and correctness. And there's a lot of future work to be done on this. But in the interest of time, I'm going to skip over that and will now like to take questions.
So, just a quick question about the Idris parser, which I'm not aware of. Is it a char parser or is it a token parser?
It is a token parser.
Do you foresee any difficulties for LR parsing, because you don't mention that explicitly?
The previous iteration of this work was doing this exactly on LR parsing, so that works. The math is a lot more complicated. This one's actually fairly trivial compared to that one, but it works.
More questions?
Yes. So this is a PEG technique rather than Parsec technique been implemented in Parsec?
Yes.
So we could take the everything from the paper, just use it on any of our big libraries?
Yes, we're in the process of porting this, or we have ported it. We're working on cleaning up the code to port this to Trifecta, which is also a PEG-style parser. But this should work for any PEG.
So we're talking about porting this to code. Do you see a way to port the notions you have to a variant of the Haskell spec so that we could now say we have a spec that doesn't specify this bizarre function?
Well, I take the formalism, basically, that I gave at the beginning of, oh, here's this, the indentation of the non-terminal is greater than or equal to. I'd specify it in terms of that.
I have a request for more future work. I see a lot of student code written in languages that are not indentation sensitive, and the students are also not indentation sensitive. The code looks terrible. Could your annotated grammars be extended to write an indentation checker that would sort of reject this badly indented code, at the point of entry to say, sorry, nobody's going to read your code until it obeys the indentation rules?
Yes, that should be fairly simple. You're basically saying, hey, we've got both explicit delimiters and indentation delimiters, and that would work perfectly within this construct.
Follow-up question, what are you doing this afternoon?
I guess working on this.
Finishing Trifecta so we can put it in Idris for real.
It's almost there. I have to talk to some of the Trifecta people because there's some questions I have. If any of the Trifecta people are in here, I do want to talk to you after this talk.
All right. Thank you, Michael.
Break.